Welcome. Today our discussion is on electric field lines and the superposition of electric field. So electric field lines depict the magnitude of a charge. So the higher the magnitude of a charge, the higher the number of lines the electric field would have. So if a charge has a higher magnitude, the number of lines of the electric field will be high. And if the charge has a lower magnitude, the number of lines will be lower relative to the magnitude of the charge. Looking at this diagram, the right charge has twice the magnitude of the charge on the left, meaning the magnitude of that charge is high compared to the one on the left. So the right charge has more electric field lines than the left charge since its magnitude is high. So this is how electric field lines are depicted. They show the magnitude of the charge. So the higher the magnitude, the higher the electric field lines, and the lower the magnitude, the lower the electric field lines. Now, the next thing we talk about is combination of charges. And with this diagram, we can see that there are two charges being brought together. And the diagram shows how the electric field lines are connected and how they move from one charge to the other. So, when a positive charge is brought near a negative charge, the field lines move from the positive charge to the negative charge. So, as we can see in the figure A, you can see that there are two charges. One is positive, one is negative. And the electric field lines are moving from the positive charge to the negative charge. So when two charges with opposite sides are brought together, the field lines move from the positive charge to the negative charge. Since we learned earlier on that positive charges have the electric field lines moving outwards, and negative charges, they have their field lines moving inwards. So as shown in the figure A, the positive charge electric field lines are moving out of the charge, and the negative charge, the field lines are moving into the charge. So when they are brought together, the field lines move from the positive charge to the negative charge, as we learned earlier on. And when the charges are equal, that is when they have the same magnitude, meaning they will have the same number of electric field lines. So when the electric field or when the charges have the same magnitude, they will have the same electric field lines. So the number of lines moving out of the charge will be the same number of lines moving into the charge. Now, when we have two charges of opposite sides and one has a higher magnitude than the other, the one with the higher magnitude will have its field lines being greater than the one with a lower magnitude. And with that, if, as shown in figure B, the positive charge with higher magnitude has a lot of electric field lines, and negative charge with a lower magnitude has few electric field lines. So the lines entering the electric field, or the lines entering the negative charge, will be lesser than the lines coming out of the positive charge, since its magnitude is smaller than the magnitude of the positive charge. And when two equal charges are brought together, their electric field lines would never meet, since there will be a repulsive force between the charges, meaning the electric field lines cannot meet, creating a space between them. And between that space, there will be no electric force exerted at that space. There will be no electric field at that space. So the electric field at that space would be zero. Electric field at that space would be zero. Now, electric field is represented with lines to show the direction of the field. The electric field are depicted with lines, and these lines have arrows on top of them, which shows the direction at which the field is moving. And as we move away from the charge, the intensity of the charge decreases, or the intensity of the field decreases. As we move away from the charge, the intensity of the field of the charge decreases. So the higher distance away from the charge, the lower the electric field. As we saw earlier on, that electric field is equal to KQ over R squared. So the electric field is inversely proportional to the distance separating the charge and the point on the field. So the higher the distance between the point on the field and the charge, the lower the intensity of the field. Now, we will look at electric flux, and this measures how much electric field vector penetrates through a given surface. So if you have a surface enclosing the electric field, and you want to know the amount of electric field vectors which will penetrate through that surface, that amount gives us the electric flux of that surface. So electric flux through an enclosure surface around the charge is the same. So EA times AA equals EB times AB. So this equation was generated from this diagram. So we have two surfaces, A and B, and the electric flux for A is equal to the electric flux for B. So for surface A, the electric flux for surface A is the electric field times the area of the surface, and the electric flux for surface B is the electric field times the area of the surface B, and they are equal since the same number of electric field lines coming out of the two surfaces, meaning they have the same electric flux. And the magnitude of the electric field on a spherical shell is constant. That is, if the field lines coming from the charge is 10, and we are having two surfaces enclosing the field lines, the magnitude of the field will not change, since it's the same field lines at which we've drawn or we've imagined two spherical surfaces around it. So we are supposed to take key note of that. Now the next thing we will talk about is superposition of electric fields. Superposition of electric fields. So as was shown in electric forces, electric field can also be superposed. That is, electric field at a point can be determined by resolving the electric field into its components, and the net electric field can be determined by summing up the constituent electric field vectorially. So as was done earlier in electric forces, if there are two or more electric field, or if there are two or more charges placed linearly or angularly, the electric field at a point from each charge can be determined using the vectorial summation of electric fields. So we apply the same concept for electric forces in electric field. So looking at this diagram here, there are two charges placed linearly, but from the Cartesian plane they are placed on the y-axis, one found on the positive, one found on the negative. And there's a point P that we are supposed to find the net electric field that each charge is having at that point. So we are supposed to find the electric field that charge Q2 has at point P and charge Q1 has at point P. So with that, we take into consideration the direction of the electric field. And before we can do that, at point P, we assume that there's a test charge at point P. So at point P, before we do that, we assume that there's a test charge at point P. And we said earlier on that, so a test charge is a positive charge that helps us to find the magnitude of electric field from a distance away from the charge. So at point P, we assume there's electric field. We assume that there's a test charge here. So if we take charge 1, which is negative, and point P here, you will note that the electric field line will be moving towards the charge. So this is how our electric field direction will be. And if we look at charge 2, which is positive, at point P, the electric field lines will be moving away from the charge. So you are supposed to note that. And with this, we resolve the electric field to this imaginary x-axis to get our net electric field. So we find the x component of E1, then y component of E1, then x component of E2, then y component of E2 to give us the net electric field. So we use the same principle that we use in superposition of forces to go by this problem as well. So we are supposed to know the distance between the point and the charge. We are supposed to know the angle that we'll be resolving at, and all the necessary information that we are supposed to know for the solution of the problem. You're supposed to jot and point out all of that. Now let's look at an example for this electric field superposition. Two charged objects, plus 10 nanocoulomb and plus 15 nanocoulomb, were placed 4 meters apart. Calculate the electric field at point P, which is 3 meters away from charge 1, as shown in the diagram below. So now, looking at this diagram, you can see that the charges were placed linearly, but the point on the electric field is placed at an angle to the charges. It's placed at an angle to the charges. And we are supposed to find the electric field at point P. So let's look at how this problem would be solved. So the first thing we will do is to state out the main equation. So we will state out the main equation for electric field, which is E equals K over R squared. K over R squared. But two charges were given in the question. So we will have two electric field equations, which is E1 and E2. So our E1 will be KQ1 over R1 squared from the diagram here. And E2 will be KQ2 over R squared. So E2, the distance for E2 is R, because from the charge Q2 to the point P, this distance is shown as R. So here is our R1, here is our R2, and here is R, meaning you're supposed to resolve this distance to get it using the Pythagoras theorem. Now, after we finding the E1 and E2, we now resolve them into their components. That's the X component and the Y component. And for the resolution, E1x will be equal to 0, because from this diagram, there is no S component for Q1. There is no X component for Q1. So our E1x will be equal to 0. And E1y will be equal to E1, since the charge 1 has only Y component for its electric field. So E1y will be equal to E1. So we take key note of that. Then now our E2x, resolving electric field 2. Our E2x from this diagram, this is our X component and this is our Y component. This is our X component and this is our Y component. Now, assuming a Cartesian plane here, we can see that the X is negative and the y is positive, meaning the x component of E2 will be negative and y component of E2 will be positive. So our E2x will then be equal to minus E2 cos theta. It is cos because the angle is adjacent to the x component. The angle is adjacent to the x component. So we will use cos as the trig function here. And for E2y, it will be equal to E2 sin theta because the angle is opposite to the y component. So it will be E2 sin theta. Now, after resolving each electric field, we then sum up the x component and the y component. So our Ex will then be equal to E1x plus E2x. Then our y component will be equal to E1y plus E2y. So we sum the x component and the y component. Then after that, we resolve it with this equation. That is E equals square root of Ex squared plus Ey squared. Square root of Ex squared plus Ey squared. So now we've noted out our necessary equations that will be used in solving this problem. Now we are supposed to resolve the side or the distance between Q2 and point P. We are supposed to resolve the distance between Q2 and point P. So we know that R squared is equal to R1 squared plus R2 squared. Therefore, our R will be equal to square root of R1 squared plus R2 squared. So substituting our values for R1 and R2, we are getting R to be equal to 5 meters. We are getting R to be equal to 5 meters. And now we are supposed to find the angle at which we resolve our component. We are supposed to find the angle at which we resolve our component. And therefore, the trig function we are using here is tan. So theta will be equal to tan inverse of R1 over R2. Will be equal to R1 over R2. Since we know that tan is opposite over adjacent. Tan is opposite over adjacent. Our R1 is opposite to the angle and R2 is adjacent to the angle. So after substituting our values for R1 and R2, we are getting theta to be equal to 36.9 degrees. Theta to be equal to 36.9 degrees. We then calculate or do our substitutions and find out all the values necessary for the calculation. Firstly, we go for E1. So we substitute necessary values K, which we know to be 8.99 times 10 to the power 9. Then Q1, 10 times 10 to the power minus 9. So nano is to the power minus 9. Then our distance for R1 is 3. So we square that. Then we are getting 9.98 Newton per Coulomb. Now we move to E2. We do the necessary substitutions. So E2 is equal to 8.99 times 10 to the power 9 times 15 times 10 to the power minus 9 all over 5 squared. And E2 is giving us 5.39 Newton per Coulomb. So now back to our resolutions. E1x is equal to 0, as we emphasized that earlier on. Then E1y is equal to E1. Therefore, equals 9.98 Newton per Coulomb. Now to E2x, which is minus E2 cos theta. So we do the substitutions. E2 is 5.39 cos 36.9. Therefore, giving E2x minus 4.31 Newton per Coulomb. Giving E2x minus 4.31 Newton per Coulomb. Now E2y equals E2 sin theta. Substituting the values, we are having 5.39 sin 36.9. Therefore, E2 equals 3.24 Newton per Coulomb. So now we've resolved the x and y components for E1 and E2. So we therefore sum the values for EX and EY. So EX equals E1x plus E2x, which is 0 minus 4.31. Therefore, EX equals minus 4.31 Newton per Coulomb. EX equals minus 4.31 Newton per Coulomb, as shown here. Then our EY equals E1y plus E2y. Doing that substitutions too, we're having EY equals 9.98 plus 3.24. So therefore, our EY is equal to 13.22 newtons per coulomb. So we therefore resolve our E, which equals square root of ES squared plus EY squared. So substituting our values, we are having E equals square root of minus 4.31 squared plus 13.22 squared. So therefore, our net electric field equals 13.91 Newton per Coulomb. So at point P, the net electric field from charge Q1 and charge Q2 is equal to 13.91 Newton per Coulomb. So here is a trial question that you can try your hands on.